In this video, we're going to talk about linearly independent vectors, and we're going to focus on the definition. So vectors u1 up to uk are linearly independent if the following holds. So if c1u1 plus c2u2 all the way up to ckuk is equal to the 0 vector, then c1 is equal to 0, c2 is equal to 0, all coefficients are 0 up to ck is equal to 0. So in other words, the only solution to this equation is the trivial solution in which all coefficients are 0. So this equation has only the trivial solution. Now we have to be a bit careful here. This definition is a little bit subtle. It is an if-then. It's an implication. If this is true, then this is true. Now, certainly, if I take all coefficients to be 0, I'm going to get the 0 vector. This is not special. This is true for all sets of vectors. If you take all coefficients to be 0, you will get 0. But for linearly independent vectors, what we're saying is the only way for this to be equal to 0 is for all coefficients to be 0. So if you do see a linear combination of linearly independent vectors equal to the 0 vectors, then all coefficients must be 0. There are no other solutions. Now, if a set of vectors are not linearly independent, then they are linearly dependent. But we can be a bit more precise than that. So vectors u1 up to uk are linearly dependent if there are scalars c1 up to ck, at least one of which is non-zero, such that this equation holds. And the key here is at least one of which is non-zero. So in other words, this equation has a non-trivial solution. So there is a non-trivial solution. Now, we're not saying that none of the coefficients can be 0. You can still have 0 coefficients. The key is that at least one of the coefficients is non-zero. So for example, if we have vectors u, v, w, and z, for which 3u minus 2v plus root 2w plus 0z is equal to the 0 vector, then we can conclude that u, v, w, and z are linearly dependent. They are linearly dependent because we have a linear combination of these vectors equaling 0, and at least one of the coefficients is non-zero. So we have a non-trivial solution. Okay, so now let's see how we can determine whether or not some vectors are linearly independent. So here we want to know, are these vectors linearly independent? And in this video, we're going to check this using the definition. In the next video, we're going to use a little bit of theory to answer this question. So what we want to do is we want to start by taking a linear combination of these vectors and setting them equal to 0. So we're going to suppose that A times 1, 0, minus 1 plus B times 2, 1, 2 plus C times 3, negative 2, 0 is equal to 0. So it's the 0 vector, so 0, 0, 0. And this will be for some, so this will be for some A, B, and C in the real numbers. So some scalars A, B, and C. So we will suppose that we have a linear combination of these vectors equal to the 0 vector. And now we want to know how many solutions this system has. Do we have only the trivial solution, or does there exist a non-trivial solution? Now, to figure this out, we will notice that this is equivalent to solving this system of equations. So we get a system of equations by looking at the entries. So here we would get A plus 2B plus 3C is equal to 0. So A plus 2B plus 3C is equal to 0. And then we're going to get another equation here from the second entry. So this will just be 0. B minus 2C is 0. So B minus 2C is equal to 0. And negative A plus 2B, this will be 0, is equal to 0. So negative A plus 2B is equal to 0. And we want to know, again, still, how many solutions? Does this have only the trivial solution, or does there exist a non-trivial solution? So let's solve this system of equations, and we can do this by row reduction. So I'm going to put 1, 2, 3, 0, 0, 1, negative 2, 0, negative 1, 2, and 0, 0. So this is the augmented matrix for this linear system of equations. And here, so this will be the column for A, this is for B, and then the last one, this will be for C. So now let's solve this system of linear equations. And so we're going to do a bit of row reduction. All right, so now I have a leading one already here, so I'm going to use it to create zeros below. So to do that, I'm going to take, in this case, row 3 plus row 1. So I'm going to get 1, 2, 3, 0, 0, 1 minus 2, 0. And now, so this plus this is 0. 2 plus 2 is 4. And 0 plus 3 is 3. And then the last column just stays as 0. So now again, I have a leading 1. To answer this question, I am going to go all the way to the reduced row echelon form. In the next video, I'll talk about going just to a row echelon form. But for now, I'm going to row reduce all the way to the reduced row echelon form. So I'm going to take this 1, and I'm going to use it to create zeros above and below. So here I'm going to go row 1 minus 2 row 2, and row 3 minus 4 row 2. So row 2 I'm just going to recopy down. And now I'm going to take this minus 2 of these is still 1. This minus 2 of these is now 0. So 3 minus 2 of these, so that's plus 4, so that will be 7. And 0 minus 2 of these, that's of course still 0. All right, so now here we want to take row 3 minus 4 row 2, so that's still going to be 0. This minus 4 of these is now 0. 3 minus 4 of these, so 3 plus 8, that will be 11. And then 0 minus 4 times 0 is still just 0. Okay, so now I do have, in this case, I have obtained a row echelon form, and I will actually be able to answer the question from this form, but again, for the purposes of this video, I'm going to keep row reducing. So just be aware that you do have the option of stopping once you obtain an REF. So now I'm going to create a leading 1. So 1 over 11 row 3. So 1, 0, 7, 0. 0, 1, minus 2, 0. 0, 0, 1, 0. And again, to get to a reduced row echelon form, I'm going to use this 1 to create zeros above. So do be careful if you are trying to obtain a reduced row echelon form. One of the most common errors is to forget to create zeros above our leading ones, especially in this last step. So do keep an eye out for that. So I'm going to use this to create zeros above. And so now I'm going to take row 1 and minus 7 row 3, and that will produce a 0 here. And if I take row 2 and add 2, then, oops, that will give me, if I add 2 row 3, that will give me a 0 here. There we go. Okay, so let's copy down row 3. And so now row 1, so this minus, oh, I didn't write down that row up. So let me quickly do that. So row 2 plus 2 row 3. There we go. Okay, so this plus this is still 1, of course. So 0 minus 7 times 0 is still 0. 7 minus 7 is now 0, and 0 minus 0 will remain 0. And now for row 2, so here we're going to take this plus 2 of these. Well, that's still 0. This plus 2 of these is still 1. And negative 2 plus 2 is now 0. 0 plus 2 times 0 is 0. So we've obtained the reduced row echelon form. And we can see here, I'm going to identify my leading entries. And so the solution to this system is that A is equal to 0, B is equal to 0, and C is equal to 0. So we have a unique solution. So this is the only solution, is the trivial solution 0, 0, 0. So this is the only solution. So our conclusion is that these vectors are linearly independent because the only solution of this linear combination being equal to the 0 vector is for all coefficients to be 0. So our conclusion is, therefore, V1, V2, V3 are linearly independent. We had a unique solution, and it's 0, 0, and 0. Okay, so let's take a look at another example. We're going to ask the same question. So are these linearly independent? And we're going to set it up in the same way. So we're going to take a linear combination of our vectors and set them equal to 0. So again, I'm going to suppose that A times 1, 2 plus B times negative 1, 3 plus C times negative 3, 4 is equal to the 0 vector. In this case, we're in R2, so the 0 vector is 0, 0. And again, this will be for sum. So we have 3 scalars, A, B, C in R. And again, we want to know how many solutions are there? Do we have only the trivial solution, or does there exist a non-trivial solution? So once again, we're going to solve this by solving the equivalent linear system. So in this case, we have 2 equations. So we're going to get A minus B minus 3C is equal to 0. So that's our first equation. A minus B minus 3C is equal to 0. And then 2A plus 3B plus 4C is equal to 0. So 2A plus 3B plus 4C is equal to 0. So let's solve this. So again, we're going to put this into a matrix. So 1 minus 3, 0. 2, 3, 4, 0. So now let's row reduce. So we have a leading 1, and so we're going to use this to create zeros below. And so now we have row 1. So we're going to take, row 2 minus 2 row 1. So we're going to leave row 1 alone. And we will take this minus 2 of these is 0. This minus 2 of these is 5. This minus 2 of these, so 4 plus 6 is 10, and then 0 plus 0 will be 0. Okay, so again, I'm going to go all the way to the reduced row echelon form. So here I'm going to take 1 over 5, row 2, and this gives me 1 minus 1 minus 3, 0, 0, 1, 2, and 0. Now I have my leading 1. I'm going to use it to create zeros above. So one more row operation. So I'm going to take row 1 plus row 2. So row 1 plus row 2 will certainly create a 0 here. So let me recopy row 2. So 0, 1, 2, 0. 1 plus 0 is 1. Negative 1 plus 1 is now 0. Negative 3 plus 2 is negative 1, and here 0 plus 0 is 0. So now we have a different situation than what we had before. We have a leading entry here and a leading entry here, but here we have a free variable. And so if we want to solve this system, so we can recopy down the equations. So this becomes a minus c is equal to 0. So that's the first equation. This is the column for A, B, and C. So A minus C is 0. And then this one says B plus 2C is equal to 0. So here we have B plus 2C is equal to 0. So if I solve for my leading variables, so I'm going to solve for A and B. C is a free variable. There's no leading entry in its column, so we assign C a parameter. So we're going to call this T. And then now solving, oops, that's a plus sign. So here we're going to get B is negative 2T. And again, bringing the C over, A is just T. So here, what we found is that we have infinitely many solutions. So we certainly have a non-trivial one, so we can certainly find one. But in this case, we do have infinitely many solutions. So we certainly don't have a unique solution. We don't just have the trivial solution. So infinitely many solutions. And now, if we want to find a non-trivial solution, certainly if we have infinitely many, we have at least one non-trivial one. So let's actually find one. So if we want to find a non-trivial solution, then I can take T, for example, to be, let's say, 1. I can take T to be anything other than 0. If I take T to be 0, I'm just going to get that trivial solution. So if I take T to be 1, then I would have the solution. So A would be 1. So remember, what does this represent? A was the coefficient on the vector 1, 2. So I'm going to get 1 times 1, 2. B was the coefficient on the vector negative 1, 3. So if I plug in 1, I'm going to get negative 2. So again, I'm taking T to be 1, so I'm going to get 1, negative 2, 1. So this is the coefficient negative 2. So negative 1, 3. And then C is 1, and that's the coefficient on negative 3, 4. So this would be plus 1 times negative 3, 4 is equal to 0. So indeed, I do have a non-trivial solution. So 1, negative 2, 1, this is indeed a non-trivial solution. So my conclusion here is yes, there is a non-trivial solution. There is a non-trivial solution. And so the conclusion is the vectors, so therefore, so just so you know, when you see these 3 little dots, that's short form for therefore. little triangle form. So therefore, the vectors, to answer the question, the vectors are not linearly independent. They're not linearly independent. They are linearly dependent. So they are linearly dependent. So that's how we can check using the definition whether or not a set of vectors are linearly independent. So we set up a linear combination of those vectors equal to the 0 vector. And if we have only the trivial solution, then the vectors are linearly independent. But if we have a non-trivial solution, then those vectors are linearly dependent. And in this case, because this is a homogeneous system, homogeneous systems are always consistent. So either you have a unique solution, which in this case is just the trivial solution for a homogeneous system, or you will have infinitely many solutions. So when we're thinking about linear independence, if we have a non-trivial solution, automatically it means that we will have infinitely many solutions. And that's because here, if we have a unique solution, because it's a homogeneous system, the unique solution is the trivial solution. So let's do one more example. And we're going to do, again, the same kind of thing. We're going to use the definition, but we're going to do it in a case where we're using symbolic or arbitrary vectors. So we don't know what these vectors look like, but the process is going to be the same in terms of how we set up how we use the definition here of linear independence. So here we're going to let u and v be linearly independent vectors in Rn. And what we're going to show is that u plus v and u minus v are also linearly independent. So we're going to do a little proof, but like I said, we're going to use the definition. So when in doubt, go back to the definition. If you're not sure what to do, go back to the definition. So here, what are we going to assume? So our assumption is that u and v are linearly independent. So here u and v are linearly independent. That's our assumption. Dependent. And so we know that whenever we come across a linear combination of these two vectors equal to the 0 vector, that has only the trivial solution. So we got to keep that in mind. We're going to use that at some point here. And what we're going to show is that these two vectors, u plus v and u minus v, are linearly independent. So we're going to show that u plus v and u minus v are linearly independent. So how do we do this? Okay, so again, we're going to start the same way that we did in the cases that we knew what the vectors look like. Here we don't know what they look like, but we're going to start in the same way. So we're going to suppose that we have a linear combination of these two vectors equal to the 0 vector. So we're going to suppose that a times, so again, this u plus v is one vector, so it's a times u plus v. If we add two vectors together, that gives us another vector. So here, u plus v is just a single vector, so we take a scalar multiple of u plus v plus b times u minus v, and we're going to set this equal to 0. And again, so suppose we have this linear combination equal to 0 for some a and b in the real numbers. Okay, so now what our goal here, what we want to show that they're linearly independent, but the way that we're going to do that is by showing that a is equal to 0 and also b is equal to 0. So we're going to show a is equal to 0 and b is equal to 0. So how can we do this? Okay, so we have that A times U plus V plus B times U minus V is equal to 0. And so now we can use the distributive property, and we have that A times U plus A times V plus B times U minus B times V is equal to the 0 vector. And now we're going to gather up coefficients. So how many copies of U do we have? So we have A copies of U plus B copies of U. So that's going to be A plus B U. And then the same thing for V, we have A copies here and negative B copies here. So we have A minus B times V, and this is equal to 0. And so why did we do this? Why did we rearrange this to get it into this form? And it's because we want to use our assumption here. What we've obtained is a linear combination of our two vectors u and v equal to the 0 vector. And we know that these two vectors are linearly independent. So whenever we have a linear combination of these vectors equal to 0, all coefficients have to be 0. Now, the coefficients in this case are not just a and b. I'm not just going to set a and b to be 0. The two coefficients are a plus b and a minus b. So here, I know that this implies that a plus b is equal to 0 and a minus b is equal to 0. And again, we should justify this. Here we're using our assumption, so we should justify whenever our steps here when we're using our assumptions. And so what is the reason for this? And this is an important reason. We can't just assume this is true for any vectors. This is only true for linearly independent vectors, that this must be the case that both coefficients are 0. So this is since u and v are linearly independent. So they are linearly, and this is the important part, independent. This is why we can do this, because this implies that these must be 0. So now what we have is we do have a nice system of equations that we can solve. And so what we can do is we can stick this into a matrix and we can row reduce this. And so here I've skipped out the steps. I didn't show all of the row reduction, but we can certainly put this into a matrix and row reduce. So the first equation, so this is the column for A, this is for B, so this is going to be 1, 1, 0, and this will be 1 minus 1, 0. And so now when I use this notation here, that means that these two matrices are what we call row equivalent. So I can apply row ops from one to get down to the other. And so here I'm just skipping my steps for the sake of time for this video. But so in practice, when you're doing assignments and on exams, do make sure you show all of your row operations. So you would have to show how you can row reduce this. And so when I do row reduce this, I do obtain, in this case, again, I went all the way to the reduced row echelon form. I will talk about in the next video how you can stop a little bit earlier at an REF. But in this case, when we row reduce, we do obtain that A is equal to 0. So again, if I circle here, this says that A is equal to 0, and this says that B is equal to 0. So A is equal to 0, and B is equal to 0, and this is the only solution. So it's the only solution. And so we've successfully done it. We've shown that the only solution here is the trivial solution 0, 0. And so the conclusion is, therefore, u plus v and u minus v are linearly independent. So this is using the definition. So in the next video, we are going to talk about some shortcuts to proving that things are linearly independent, especially when we know what the vectors actually look like. But when in doubt, go back to the definition. Set up a linear combination of vectors equal to the 0 vector and show that that has only the trivial solution. All right, so that's it for this video. I will stop here. Goodbye for now.